pause the video for a moment, read the problem. We're going to walk through an application problem. I hope you paused and read it. Thank you if you did. All these application problems involve us getting a solid triangle that we know at least two angles on the side or two sides in an angle or something like that. Some kind of triangle that we can then apply either law of sines or law of cosines to. Of course, so far, since all we know is law of sines, this will be a law of sines problem. But the picture is tricky, right? So let's go ahead and read this and talk about this picture. You know, just when you have something like this, I always read it a couple times, and then I kind of go through and underline stuff. So I've read it once. I know we have a flagpole on some sort of hill. The flagpole's at a right angle to the horizontal. So it looks like I'm going to need some sort of horizontal. It's on a hill that makes a 12-degree slope with the horizontal. So the next thing I might draw is a slope. I know that slope is 12 degrees. And I know that the flagpole is, of course, they say here, perpendicular to that horizontal. So it goes straight up to what would be considered horizontal. Yay. Hooray. The flagpole casts a 16-meter shadow going up the hill. So I'll go ahead and draw that in there. It's my gray shadow. It's 16 meters. And that happens when the angle of the sun, the angle of elevation to the tip of the shadow, is 20 degrees. Okay, so we have the angle of elevation from the tip of the shadow to the sun being 20 degrees. So a couple of things I do want to remind you guys of. We have a sun somewhere over here. It's going to like shine down and make a shadow. Anytime we mention angle of elevation or angle of depression, that's always off of a horizontal line. So if this is the tip of my shadow, this is going to be a horizontal line, and the angle from the sun to the tip of the shadow is 20 degrees. So this is going to be 20. Now, that's the best I can do with my picture. I had to read the problem 2 or 3 times, dissect it as I did it to get the picture right. And now my next job is to figure out a triangle in there that'll help me solve anything else I might want to solve. I'm going to guess that they're going to ask us to find the height of this flagpole. Right? So let's look for a triangle first. A few things I want to point out. We do have all these wonderful theorems from geometry about parallel lines. This line and this line are parallel to each other because they're both horizontal. This would be a transversal of some kind. This 20 degrees is not the, well, here's the triangle we want, I should say. Let's mark that up in yellow. Let's use pink. Yeah. So this is the triangle I want. And currently what I know about this triangle is I don't know, whoopsie doodles, I don't know the length of the flagpole. I don't know this length. I do know this length is 16 meters. And so far, that's really all I know for sure. But I can figure out this angle. It's not 20 degrees, right? This is 20 degrees, like to the horizontal. But the whole angle itself is not. But with these lines being a transversal and these lines being parallel, whatever angle is here is also going to be here. So we have a 12-degree angle in there. So this whole angle right here is 32 degrees. Fantastic. I have one side and one angle. I want to figure out the height. I still need more information about this triangle, this purple one that I drew over here. So maybe pause and think about it for a minute. Where else can we get information about this triangle? And the only other thing I really know for sure is that, like, that flag is definitely perpendicular to the horizontal. So that's kind of a clue. I'm standing here like an idiot because I'm hoping you're pausing and thinking. So pause and think about that for a minute. Okay, hopefully I'm unpaused and my face no longer looks weird. If this is 90 and this is 90 and this is 12 degrees, I can figure out what this is. It's whatever's left of the triangle itself. Just so I don't make any dumb mistakes, I won't do this math in my head. This has to be a 78-degree angle here. And these guys are vertical angles. So this has to be a 78-degree angle here. Let's zoom in on my new triangle to knock this problem out. So my goal is to analyze the picture and just try to figure out as much information about a triangle that I can, and I'll solve this triangle to do it. And I do finally have enough information. I know this is 78 degrees, and I basically have two sides two angles and a side. I have an angle, side, angle case. So when we're knowing both laws eventually, I'll want you to know, oh, if it's angle, side, angle, that's a place where we use law of sines. And this is what we're trying to figure out, is this fella over here. So since they gave me this side over here, these angles are great, but this is the one I really am going to need to figure out if I want to use this side. So that's also what's left of 180. So I'll just go ahead and do 180 minus the sum of these two angles. So this is going to be a 70-degree angle. And now it's simply a matter of saying, well, I'm going to use a version of law of sines that puts the sides on top because I want to know a missing side. So we'll say f over the sine of 32 is equal to 16 over the sine of 70. And then to solve this, of course, it's f divided by some gross number equals whatever number this ends up being. Anytime I want to get rid of something when it's been divided, I multiply. So I'll multiply both sides by whatever this number ends up being. It'll look like this, 16 times that number I don't know just yet, all divided by the sine of 70. I definitely recommend you guys enter this kind of thing in your calculator rather than getting a value for this and approximating it. If you start rounding early in these problems, things go really badly. So now I'll just enter in the calculator. I'll make sure I'm in degree mode. 16 times the sine of 32 divided by the sine of 70. And I get an answer. Oh, meters. I'm like, that's a pretty small flagpole. It's only 9. I guess meters that's pretty big then. So it's approximately 9.023 meters, which I think is around 27 feet maybe. I don't know. It's pretty big. All right, so look at all that fun geometry we use. We use vertical angles, we use parallel lines, and transversals, you know. But the laser-like focus that I had was get myself a triangle and try to find two sides and an angle or two angles and a side or whatever I can, and then apply the appropriate rule. All the application problems are really about getting that drawing done well. So I hope that helps you guys out, and good luck with the other application problems.